K-means clustering. Let us say we have an image that is stored with 24 bits per pixel and can have up to 16 million colors. Assume we have a color screen with 8 bits per pixel. That can display only 256 colors. We want to find the best 256 colors among all 16 million colors, such that the image using only the 256 colors in the palette looks so close as possible to the original image. This is a color quantization, where we map from high to lower resolution. In the general case, the aim is to map from a continuous space to a discrete space. This process is called vector quantization. Of course, we can always quantize uniformly, but this wastes the color map by assigning entries to colors not existing in the image, or would not assign extra entries to color frequently used in the image. For example, if the image is a seascape, we expect to see many shades of blue and maybe no red, so the distribution of the color map entries should reflect original density as close as possible, placing many entries in high density regions, discarding regions where there is no data. Let us say we have a sample of x, which is equal to the set x to the t, where t is starting from 1 to n. We have k reference vectors, and j is the index starting from 1 until k. In our example of a color quantization, x to the t are the image pixel values in 24 bits, and mj are the color map entries also in 24 bits, with k equals to 256. Assume for now that we somehow have the mj values. We will discuss how to learn them shortly. Then, in displaying the image, given the pixel x to the t, we represent it with the most similar entry, mi, in the color map, satisfying that x to the t minus mi, whose absolute value is equal to the minima of x to the t minus mj, where minima is taken among all possible j. That is, instead of the original data value, we use the closest value we have in the alphabet of reference vectors. Mi are also called codebook vectors or code words because this is a process of encoding-decoding. See figure 7.1. Going from x to the t to I is a process of encoding the data using the codebook of mi, I from 1 to k, and on the receiving end generating mi from I is decoding. Quantization also allows us compression. For example, instead of using 24 bits to store or transfer over a communication line, each x to the t, we can just store or transfer its index I in the color map using a bits to index any one of 256, and we get a compression rate of almost 3. There is also the color map to store transfer. Let us see how we can calculate mi. When x to the t is represented by mi, there is an error that is proportional to the distance. That is xt minus mi, the absolute value. For the new image to look like the original image, we should have these distances as small as possible for all pixels. The total reconstruction error is defined as the expectations of the set of mi, where I is starting from 1 to k, conditional x, which is equal to the doubling summations of summing t and summing I of the term. That is bi to the t times the square of the distance between x to the t minus mi. Figure 7.1 is that given x, the encoder sends the index of the closest code word, and the decoder generates the code word with the received index as x prime. Error is x prime minus x, then to the square. Now, where bi to the t in the previous formula is equals to 1 if x to the t minus mi is equals to the minima of xt minus mj, where the minima is taken among possible j, and bi to the t is equals to 0 otherwise. The best reference vectors are those that minimize the total reconstruction error. Bi to the t also depend on mi, and we cannot solve this optimization problem analytically. We have an iterative procedure named k-means clustering for this. First, we start with some mi initialized randomly. Then, at each iteration, we first use equation 7.4 and calculate bi to the t for all x to the t, which are the estimated labels. If bi to the t is 1, we say that x to the t belongs to the group of mi. Then, once we have these labels, we minimize equation 7.3. Taking its derivative with respect to mi and setting it to 0, we get mi equals to the summations of bi to the t times x to the t summing for index t divided by the summations of bi to the t summing for index t. The reference vector is set to the mean of all the instances that it represents. Note that this is the same as the formula for the mean in equation 7.2, except that we place the estimated labels, bi to the t in place of the labels ri to the t. This is an iterative procedure because once we calculate the new mi, bi to the t change and need to be recalculated, which in turn affect mi. These two steps are repeated until mi stabilize. See figure 7.2. The pseudocode of the k-means algorithm is given in figure 7.3. One disadvantage is that this is a local search procedure and the final mi highly depend on the initial mi. There are various methods for initialization. One can simply take randomly selected k instances as the initial mi. The mean of all data can be calculated and small random vectors may be added to the mean to get the k initial mi. One can calculate the principal component, divide its range into k equal intervals, partition the data into k groups, and then take the means of these groups as the initial centers. Figure 7.2 evolution of the k-means. Crosses indicate center positions. Data points are marked depending on the closest center. Now, after convergence, all the centers should cover some subset of the data instances and be useful. Therefore, it is best to initialize centers where we believe there is data. There are also algorithms for adding new centers incrementally or deleting empty ones. In leader cluster algorithm, an instance that is far away from existing centers, defined by a threshold value, causes the creation of a new center at that point. We discussed such a neural network algorithm, ART, in Chapter 12, or a center that covers a large number of instances. The summations of bi to the t summing for index t divided by n, which is greater than theta, some threshold, can be split into two by adding a small random vector to one of the two copies to make them different. Similarly, a center that covers too few instances can be removed and restarted from some other part of the input space. K-means algorithm is for clustering, that is, for finding groups in the data, where the groups are represented by their centers, which are the typical representatives of the groups. Vector quantization is one application of clustering, but clustering is also used for preprocessing before a later stage of classification or regression. Given x to the t, when we calculate bi to the t, we do a mapping from the original space to the k-dimensional space, that is, to one of the corners of the k-dimensional hypercube. A regression or discriminant function can then be learned in this new space. We discuss such methods in Chapter 12. Figure 7.3 is the k-means algorithm. Initializes mi starting from 1 to 3 until k, for example, to k random x to the t. Then we do the following repeat until mi converge. For all x to the t in x, we let bi to the t equals to 1 if x to the t minus mi is chosen among all possible minima x to the t minus mj, where the minima is taken among all possible index j, and the bi to the t is equal to 0 otherwise. Then later on, for all mi I starting from 1 to k, we re-update mi as the value of the summations of bi to the t times x to the t, summing for index t, then divided by the summations of bi to the t summing for index t.